Okay, folks, here we have the part B of the self-driving car and autonomous vehicle section. This is all in the part which is dealing with the autonomous vehicles. And here we're going to do some more detail about the AI technology and the role of AI, which is actually the heart of the problem. It's the really hard problem. There's lots of other important problems, but they're not really as totally challenging. All right, so here is a sort of starting point, and there's a huge number of blogs and articles and tutorials and things. I subscribe to medium.com. I get several articles a day just from medium.com. And here is a review of the actual sort of industry battle going on with all sorts of parts of the industry, the actual automobile industry, various other things, including Waymo, which are parts of Google, and parts of Apple and parts of Facebook. They're all competing in this area, and the ride-hailing companies have a major activity because they're all people who want to be a major player in this emerging mobility industry. And here we have a nice presentation from Princeton about the issues. Here is a more specialized article on cybersecurity. We really don't want people to be able to hack into our cars when we're doing something dangerous. The Nvidia, we'll mention them a little next 2 or 3 slides. They have a nice open source network for self-driving cars. And here is a paper on it, and here is a tutorial on it. And here is yet another tutorial. Then if we are trying to sort of do the AI, we have to do lots of things. And these 4 things here are certainly 4 of the most important. We have to position the car in the right place. We have to decide how to drive, path planning. That is both tactical, get around the corner, and strategic, get from A to B a million miles away. Then we have to detect objects, the cars, the people, the sides of the roads. And then we also have to tell the road signs. These all have to be done in very quickly. People do it extremely quickly, seconds, or order of a second sort of delay, and cars have to match that time. So these requirements are all real time, and you can't afford to put any delay. So these decisions are all largely made on the car itself. The training, the design of the network can be done offline and can involve so-called cloud computing or data center computing. All right, so here we have a piece of hardware that Nvidia built their tutorial around with 3 cameras, left, center, and right. There's a disk to store all the training data, which we use for all the model data, which we use to inference, or training data, which we use if we're trying to build the model. And here's the model starting at the bottom here. That's the input. We have 66 by 200 pixels, each in RGB. So array 3 in the RGB space. And then we roar up through classic CNN so-called convolutional networks, which are identifying the structure in the image. And then we get to sort of fully connected networks at the end, which extract information. See, we have fully connected convolutional. 1, 2, 3, 4, 5 convolutional parts, and here we're just normalizing the input data. Okay, so we will go into what all this stuff here means in the technology talk parts of this class. Okay, here is the logic of Nvidia's tutorial. The ultimate goal is to change the position of the steering wheel so the car is driven in the right way, and we take the data from the 3 cameras, feed it in, we do shifts and rotations. That's a standard trick to generate more data by taking existing data and moving them around. Like if you want to be certain to recognize a cat, however the cat is, whatever the angle the cat is in the image, or whatever the distance, you take one photo and then you just rotate it and put it into the distance and things like that. And so here we have the training, and then that train tells you the model, namely the value of the neural network weights in this picture we had on the previous slide. Then in the inference, we take just the center camera. I'm not quite certain why we don't use the left and the right. Feed it into the model and get out the instructions. Okay, here is a typical of what these cameras will tell you. They will tell you the lanes. They will tell you things on the road. And they will tell you road signs. And these road signs are directional and also speed. And you better know whether the speed is miles per hour, kilometers per hour, or whether it's just the name of the road, US 55 or Beijing into Highway 55 or wherever we happen to be. Okay, so there is an amusing article, maybe amusing by who wrote this, by a high school student who's proud that he's not allowed to drive because he's not old enough, but he can teach cars to drive. There's no age limit on that. And this particular article distinguishes rule-based and learning-based driving. Learning just takes the input and trains the car to do the same as the human. Rule-based is more systematic. It takes the input, divides it up into these different things, the traffic sign, the cars, the pedestrians, planning the path, and then it designs the output. This article is built around Steve, the Nvidia system we described, and there is another article I noted here, a totally different one on sensors, which is pretty useful. So there's just lots and lots of articles. And I didn't mention here the one which is suddenly obvious to me when I try to drive my car. Driving in bad weather is terrible. And pelting rain, snow, that make driving very hard. All right, so here's an amusing picture to show that Jaguar wants their cars to be loved, and maybe people don't love self-driving robots because they're not human, and so they design their car to be such that people love them. And they not only pay AI engineers, but they pay cognitive psychologists to design their next generation self-driving cars. So this is a UK auto drive project. That sounds like a self-driving project. Here's Mercedes-Benz, a much more classic, smooth picture of a beautiful car, smooth, nicely aerodynamically designed to go real fast. Here is Otto, which is Uber's self-driving truck. I think it has a driver in there. Presumably that's required at the moment. And there's just lots and lots of these pictures on the web, and actually things existing of prototypes in this field. Right, here we illustrate another aspect of self-driving transportation, namely here we have some road-making equipment or equivalent. And here actually there's probably a lot of promise, because the building a road is much more or building something new involving bulldozers and stuff. It's much more systematic than driving, because you just have a few vehicles which are going to have to interact with each other. You have a plan and a goal which is agreed. And so to be able to use autonomous vehicles in this road construction industry is likely to be highly promising, and one deployed before the general transportation effort. All right, so that's that. It's pretty interesting. You could follow up on this and other. There, of course, this is not the only activity in this area. I went to a conference in China at one stage, which had a large emphasis on this, and they made lots of progress. Thank you. Everybody has prototypes. Here's an interesting thing I found on medium.com by the Chief Executive Officer John Krafkick of Waymo, and they just announced that their vehicles have driven 10 million miles on public roads. A lot of those, presumably most of them, had actually compulsory humans in the car to correct if the self-driving car went bonkers. And of course, that 10 million miles is what put into the network, and it's more driving than a human would have. Humans learn to drive with just, I don't know, hundreds at most of miles of driving. However, they're given a lot of, effectively, they do transfer learning. They're given some information by people who've already learned to drive. And the millions of miles were driven in 25 cities, including, they claim, the snow. And they go from the cities to the rural areas. But they also have done 7 billion, which is almost 1,000 times as much, driving of simulated data. So when you're designing a network, you can either take real data, observational data, or you can actually write a computer program that generates the data. And it's actually very common in deep learning to use simulated data. The advantage of simulated data is somewhat easier to get the correct training, because when you have a simulated data, you certainly know exactly the right thing to do, because you know what the scenario is, and you know the best thing to do. Whereas if you actually train it to look like humans, the human may not drive correctly, so you might not train it correctly. Anyway, there's really interesting that we almost have 1,000 times much simulated data as real data. And what they point out, there's this technique called fuzzing, which is to take an existing situation, which is, say, a real situation, and then you apply a little computer program to fiddle around with the data. I already gave you an example of that about rotations. One thing you can do with data is to rotate the aspects. Now, cars shouldn't get rotated. They're the same car. Cars have to have wheels on the ground, so that particular transformation is not relevant. It's relevant for cats, but not cars. And so you can also get sort of corner cases, rare scenarios, and check that the software responds correctly. And Tesla has 1.28 billion miles on autopilot, because they have the advantage. They've sold quite a few cars, and presumably they're secretly recording a lot of the data from these cars and using that to train their networks. Okay, so this is a slide on the future of the automobile industry. We've already pointed out one of the reasons we're doing this in the class is this whole industry is getting changed. And here's yet another comment on the fact that people are giving up their own vehicles. And here we have just Lyft, which is the smaller of the US company, said 250,000 of its passengers actually have sold their own vehicle or decided not to buy a new vehicle because they're going to do ride-hailing. If you look at AI, AI can drive the car, but it can also reduce production costs and interact with the automobile industry at all aspects of its operation. And if you look at the entire sort of chain from design of a car to selling and selling the car, then AI is meant to be able to save a lot of money, 173 billion. And presumably it will actually do that work better. And of course, the self-driving technology is going to drive the major new industries, which is the industry which create a world when you only have self-driving cars and you don't have your own self-driving car, you just hail it. And this self-driving technology is meant to be 556. I wonder how they got that. They know it's 556, not 555, or maybe even more modestly, 500 billion opportunity. And it's meant to grow at almost 40% compound annual growth. And it's 54 billion last year. And of course, AI also can be used to analyze monitors on the car, see where maintenance is needed, and also, of course, to optimize the routes. This part, the route optimization, we'll discuss more in the section on the transportation system. All right, here's some sort of interesting plot I found, which looks at where the different parts of the automobile, or let's say mobility industry, and looks at the value added, which is high or low. And it thinks that actually making traditional cars is a very low value added. It's too easy to do, it's well established, not much innovation. Here we have the self-driving hardware and software. That's a huge value added. And just using AI to improve the relationship with customers and the maintenance and things is another high value. And basically creating the future, which is a self-driving fleet of cars. And I should point out the rental car industry is also part of this mobility industry, because future rental cars will be self-driving. And here is an interesting comment about why it's good to not own your own car. So if you have a personal car, the average usage is meant to be 5%. Whereas if you have a fleet of cars which are either driven by other drivers or self-driving, the uses can be more like 50%, because it's only down when it's needed to be maintained and things like that. And so that just says that it's $1 a mile for a personally owned vehicle and 30 cents per mile for a fleet. And that's an average saving of about $7,000. And this gives you this as a service term, popularized by infrastructure as a service in computing. Here you have transportation as a service. And that, if you like, is what a mobility company offers. And this curve on the right here is a smile curve. It looks like a smile, does it not? And we want to be at the end of the smile, not in the middle. The middle has no value. All right, here we go. Here are some pictures of various quantifications of what we discussed. Here's Waymo. We already mentioned they'd driven 1 million miles total, 10 million miles, sorry, already. And here it actually only goes through 2018. And it looks at which is the number of miles in California. This is the disengagement rate, how often you have to have human intervention. So that says in 2018, the disengagement rate for Waymo was 0.09 per 1,000 miles, which says the disengagement happened around every 11,000 miles, 1,000 over 0.09. And here is a more precise version of that AI through the whole automobile industry value chain, from research and development through manufacturing. And it appears, and here we have sales and marketing and things like that. And here we have the semi and fully autonomous vehicle shipments, half a million in 2019, almost a million in 2020, going up to 2.6. I'm sure these numbers are not very accurate. Well, these probably are accurate, but well, actually they're all estimates, so they're all pretty inaccurate. But they give you a feeling for what's going on. Rapid growth, but still relatively small compared to totals. Okay, now we come to some specific industry players. First is Waymo, which is the part of Google that does self-driving and is effectively its own company. And but presumably it has Google investments, else it wouldn't be able to keep going. And it has by far the most experience of pure self-driving without some humans. If you like, Tesla might have one of the biggest experience of semi-autonomous self-driving where there is a human involved. And they launched their ride-hailing service in a modest way over a year ago. By the way, I'm speaking about early February 2020. And Waymo built both the software and the data systems. and they also designed their particular, set of LiDAR and other technologies. Remember, Tesla doesn't use LiDAR, Waymo, and most other people do. And we have a little slide somewhere later on describing why LiDAR might be a good thing to do. And we've already shown they did 10 million miles of tests. Cruise is a serious company, quite big, and purchased by GM. So GM, rather than develop their own, wisely invested in somebody who was already along that path with startup funding. And that they were actually acquired them some time ago, 2016. And they hope to soon launch their own autonomous ride-hailing service. Okay, here we have some comments on, more comments on Cruise, pointing out that it not only works with GM, but also with Honda. Car companies, well known that companies form uneasy, typically alliances with their competitors, when both they and their competitor feel that, well, it may be a shame to have Honda, but it's better to do this rather than let Tesla and Toyota or others get far ahead of both Honda and GM. So I am down to, and in fact, Honda has a non-trivial investment in Cruise. And so it's a long-term relationship. Nvidia is a major player because it builds the hardware. And as we point out, there are other hardware designs, but Nvidia is the best known of the companies building hardware for artificial intelligence based on their graphics cards, which was found actually at Indiana. This was first pointed out by Adam Coates, who worked with Andrew Ng at Stanford, that the GPUs were very good for NVIDIA GPUs are very good for deep learning. And NVIDIA works with lots and lots of auto companies, and obviously they're trying to get level 5. Everybody is. Whether it's really level 5, but I think actually it's going to be a best level 4 in the early 20s. There's not so much money initially, but they certainly expect to earn quite a bit of money by 2025, which I think is a realistic number. And also, I think for NVIDIA to invest in this area is a good thing to do, because there's a lot of money to be made there, and it's also reasonably prestigious to be a leader in this area. Here is a comment on Waymo and UPS, which is a pretty recent, January 30th, 2020. And this is pretty short term and sort of very tactical. And UPS will use Waymo's technology to do self-driving on very defined routes. I mean, if you're doing sort of warehouses and things, then you have cars and trucks and things going on exactly the same route in a reasonably safe environment, because it's just it's usually probably internal to a warehouse system or something, and so there aren't pedestrians or general public and things like that. And they claim they may move further, but this is just being done in one place, Phoenix, Arizona. And DeepMind is just used to be a company, was purchased by Google, and is where Google has puts a lot of its AI research. And we know that the autonomous truck market is going to keep on growing really fast. I bet it's actually more than 70% between 2020 and 2025. These estimates here, no, the way estimates get done, they probably get defined. They're done in defined fashion, but they're just not very impressive. I mean, they're not very reliable because there's far too many uncertainties. Who knows what? It only requires, just we saw with the coronavirus, one little bat has cost billions and tens or hundreds of billions of dollars, sent a major countries, China, into hibernation, and you can't forecast that. So there's lots and lots of uncertainties, and we really can't forecast the progress in self-driving. Here's Cruise, and they have another very recent January announcement on their Origin system, which is a concept. Notice, not a car, it's a concept. And notice what the design is. It doesn't actually have a beginning and an end, it just has a middle. And the people, it's like some taxis or some vans, it has seats facing each other in the middle. And the display is showing what's going on. And of course, you couldn't drive that legally in the US at the moment, which is why it's a concept on its way to production. And as we noted, General Motors owns most of it. Honda has a 5% stake, 5.7% stake, and it is pretty advanced, having done 1 million miles in San Francisco. And this company is worth $19 billion. Which is not bad. I mean, GM itself is only worth $50 billion, so that's pretty interesting. So I'm sure GM spent less than $19 billion. So this was actually probably the best thing GM did. And here's some totally nonsensical survey about what you want to do in a driverless car. And obviously, you probably want to do whatever you would have done anyway, and what you do on trains and other things, and you hope the ride is smooth enough to allow whatever you want to do. So I don't think that's so exciting, but it just says that you want to do everything, including texting, emailing, using your cell phone.